You've seen 3D graphics. You've probably even used libraries like OpenGL or 3.js. But have you ever wondered what's happening under the hood? Today, we're going from a high-level JavaScript canvas to a $15 microcontroller to prove one thing. 3D rendering is just universal math, and we're going to fix a massive headache along the way. This is Boondoggle Certified. So first of all, I'd like to give a shout out to this guy for making the video and the algorithm for suggesting it. He did some research, found the math that makes it all possible. Bada boom, bada bing, we're good to go. And second of all, the device in question is just your standard LilyGo TTGo. I took a vape battery, glued it to the back of it, bada bing, bada boom, good to go. Push the button and it powers on. Push the button and it powers on. Well, it's a very cheap product, so sometimes this button's actually broken. Oh, there it is, finally. So, let's get into the code. At first glance, you're not going to find much difference between them. It's just a direct translation of the JavaScript code into C++ with a couple of exceptions. On the left, we have the JavaScript in VS Code with an instance of the result running in a web browser. On the right, we have this C++ in Arduino IDE with a video of the result playing for illustration purposes. Notice something about the result on the right? Yeah, it flickers, but we'll get into that in a minute and talk about how to mitigate it. But first, I'd like to talk about what these two code bases have in common. The goal of any 3D renderer is to take a point in 3D world space, XYZ, and find its corresponding pixel coordinate, XY, on a 2D screen. This process consists of three main steps, which are identical in both our JavaScript and C++ code bases. Before we touch the code, here's the math version of what we're doing. And I'll be honest up front, I don't really speak this language fluently, but the good news is we don't have to. All it's saying is take a 3D point, rotate it sideways, and then slide it forward along the z-axis. And that's what this code is doing. It's secretly doing what the matrix shows, just written out longhand so humans can code it. Now, because we can't use object literals in C++, we're going to have to define a structure. A struct is a simple way to group related information together, like a neat little backpack where every pocket has its purpose. So what we're going to define here is vec3, that'll be our 3-point vector, and point2d, which we'll use later. Now let's take a look at the C++ version. The logic is a direct translation. The C++ version uses the float from our struct for explicit precision and standard library functions like cosf and sinf, that's cosine and sine, but for float, and the core logic remains the same. And now we get into perspective projection. This is the magic step that makes distant objects look smaller. It's done by dividing the x and the y world coordinates by the z depth. This projects the 3D point onto a 2D projection plane. And now for the viewport. After projection, our coordinates are typically normalized in the range from -1 to +1. So we must now map the normalized space to the actual pixel dimensions of the display, 0 to the width or height. And this is where we use the point2d struct that we defined earlier. The final difference lies in how we push pixels to the screen. For complex frame-by-frame rendering like 3D wireframes, drawing directly to the physical LCD can lead to tearing and a flicker as the display refreshes mid-draw. The solution to this is, you guessed it, double buffering, a standard technique where we draw the entire frame into an invisible memory buffer, or the back buffer, and then push the completed frame to the screen, or the front buffer. The best way to demonstrate this is by comparing the frame clearing function before and after the change. The top function clears the frame directly on the LCD hardware, causing a visible flash or tear as the screen updates. The bottom function clears the frame in an invisible RAM buffer, preparing the next frame without impacting the currently displayed image. So this can be done in a three-step process. The first thing we do is we create a sprite object, which we'll call SPR, and modify the setup function to initialize the sprite with the full screen dimensions, and this will allocate a block of RAM for the image data. The second thing we do is we move all drawing operations from the TFT object to the SPR object. And finally, we revise the frame function to copy the completed memory buffer to the physical LCD, eliminating the perceived flicker and triggering a redraw in the TFT ESPI library. And there you have it. We pushed through and got it done. It's the next day, but we did it. No big deal. If you like what you saw today, go ahead and like and subscribe. The GitHub link is down there, as well as the link to the original video, which I'm very grateful for. And I need to go and take a shower, so until next time.
Take my